Okay, let's unpack this. Have you ever, stared at a honeycomb and felt that instinctive wonder at its perfect hexagonal shape?
Hmm.
Or maybe traced the elegant curve of a nautilus shell and been struck by, well, a profound sense of natural order?
Absolutely. Those patterns are everywhere.
Exactly. So today we're taking a deep dive into something truly fundamental. It touches on how the universe works, how nature designs, and even how we, as humans, build and create. We're talking about the world of optimal shapes.
It's a concept that really underpins so much.
And our guide for this intellectual adventure is work called The Marvels of Optimal Shapes by Philip Randolph Lillian. Now, this isn't just some dry textbook.
Not at all.
It's a text that beautifully blurs the lines between art, science, mathematics, and even, well, philosophy. Lillian actually describes it as a multidimensional journey into the nature of perfection, efficiency, and elegance.
That's a great description.
It really delves into how these concepts aren't just abstract ideas, are they? They're tangible realities, appearing everywhere from, like, the smallest quantum entanglement to the grandest cosmic structures.
And what's truly compelling about Lillian's work, I think, is how it posits that design isn't merely about making things look nice, aesthetically pleasing or just functionally useful.
Right. There's more to it.
Much more. It suggests that design is a profound, inherent language of the universe itself, a language that elegantly connects structure to meaning.
Wow. The language of the universe.
Yeah. So our mission today in this deep dive is essentially to help you decipher that language, to extract those hidden orders and reveal the inherent beauty woven into everything around us, and indeed, maybe even within us.
And for you, our listener, the goal here is really to give you a shortcut, a genuine shortcut to being well-informed on this really captivating topic. We're going to pull out the most important nuggets of knowledge and insight from The Marvels of Optimal Shapes.
Oh, highlights.
Exactly. Sprinkle in some surprising facts, maybe a bit of humor, and keep it engaging enough to hold your attention. We want you to feel like you've just completed a truly fascinating intellectual expedition by the end of this.
That's the plan. Our aim is to ensure you grasp not just what optimal shapes are, but crucially, why they possess such profound significance.
The why is key.
Absolutely. We'll explore their presence from the subatomic realm, quantum physics, all the way up to the immense scale of cosmological structures. You'll soon realize, I think, that the universe isn't just some chaotic jumble.
It feels that way sometimes.
It can, but Lillian argues it's intricately structured by an inherent intelligence, vividly reflected in these optimal forms. It's really an invitation to see the world and design itself, not just as practical application, but as a deep philosophical concept that influences pretty much everything.
Defining the marvel. What are optimal shapes? Okay, so if we're going to dive deep into optimal shapes, we need a solid starting point. What precisely are we talking about here? When I first heard the term, honestly, I pictured something very simple, like just a perfect circle. Is that too simplistic? What exactly is an optimal form in this context?
That's a great question. And, your instinct isn't entirely off. A perfect circle can be an optimal form in certain contexts, for sure.
Yep.
But the marvels of optimal shapes defines an optimal form more broadly. It's a structure that consistently achieves the most, let's say, efficient or balanced solution, but always given a specific set of constraints.
Constraints are key then.
Absolutely key. Think of it as nature's way, or maybe an engineer's way, of doing the absolute most with the absolute least. It's about maximizing a function, maybe that's strength or capacity or flow, while simultaneously minimizing the resources used, or distortion or potential errors.
Doing the most with the least.
Mm.
That concept is really powerful, isn't it? Makes you think about how much energy we, as humans, often waste in our designs.
It does.
But are these just, like, theoretical ideals? Or do they actually exist out there in the real world?
Oh, that's the beauty of it. The source material strongly emphasizes that these aren't merely abstract ideas confined to textbooks or mathematical proofs.
Good.
Optimal forms are very much practical solutions to real-world challenges. They represent, you could say, the pinnacle of efficiency and balance in action.
Okay.
But beyond just their utility, they also serve as symbolic and revealing representations of the relentless quest for perfection and efficiency across diverse domains. It's like they tell a story about trying to get things right.
Right.
And the continuous search for and understanding of these forms genuinely propels the advancement of knowledge. It refines design principles across virtually every field imaginable. They embody efficiency, balance, and often, a kind of perfection, but always in relation to clearly defined parameters.
I'm starting to get a clearer picture now. So what are some of the consistent characteristics, the things that help us identify these optimal shapes when we see them?
Well, Lillian's work highlights several key characteristics. First, and perhaps the most intuitive one, is efficiency.
Right, we touched on that. Doing more with less.
Exactly. It's about maximizing or minimizing certain aspects. This could mean, say, minimizing surface area to reduce heat loss. Think of a sphere.
Okay.
Or maximizing volume for storage again. A sphere often wins there. Or it might involve achieving ideal ratios between dimensions, like the famous golden ratio we see in nature. These forms often provide the most elegant and effective solutions to complex optimization problems.
Optimization problems.
Yes, whether that's in engineering or pure mathematics or even, interestingly, in the design of social systems.
So it's about solving a problem in the most elegant way possible. And I imagine that elegance often ties back to mathematics, right?
Precisely. You've hit the nail on the head.
Yeah.
That brings us to the second characteristic, mathematical harmony.
Harmony. I like that.
Yeah, many optimal forms are deeply inherently rooted in mathematical principles. They embody elegant relationships, fundamental symmetries, or those mathematical constants like pi or the golden ratio, constants that we see repeatedly throughout the universe.
Do they pop up again and again?
They do. They might be the result of solving complex equations or deriving from fundamental geometric theorems, or maybe emerging from intricate numerical patterns. There's just an undeniable, almost profound beauty in the underlying mathematics that dictates these forms. It's not just about utility.
Which means, logically, they naturally excel at whatever they're supposed to do. That's functional excellence, I suppose.
Exactly right. In the practical sense, an optimal form is simply one that performs its specific function with the absolute least amount of resources or energy expenditure. Minimal effort, maximum result.
Nice.
And this principle applies universally, whether we're examining, complex biological structures in nature, like a bird's wing, or designs engineered by humans for specific tasks, like a bridge truss, or even abstract mathematical concepts that model perfect processes. It's always about achieving peak performance with minimal input, making every little bit count.
And often, these shapes just look right, don't they? There's an innate aesthetic appeal to them.
Absolutely. That's the next one. Geometric elegance. Optimal forms frequently possess a striking aesthetic beauty and visual appeal. It's not just their functional superiority that grabs us, but how they captivate our eyes.
Yeah, like that honeycomb.
Exactly like the honeycomb. Whether discovered in nature, meticulously crafted by humans, or emerging purely from mathematical constructs, these forms tend to mesmerize observers with their harmonious proportions and inherent visual appeal. There's an undeniable rightness to their appearance that somehow transcends mere utility, often invoking a sense of wonder.
But it's crucial, I imagine, to remember that what's optimal isn't some fixed universal thing, is it? It depends.
You've hit on a critical point there, context dependence. The optimality of any given form is entirely relative, completely. It hinges on the specific goals, the constraints, the criteria it's designed to serve. What's considered the most efficient or perfect solution in one scenario, say, minimizing drag for a race car, might be entirely suboptimal in another, like maximizing stability for a cargo ship.
Right. Different problems, different answers.
Exactly. This really underscores the importance of precisely defining the context when we evaluate a form's optimality. It's not a universal ideal, but a highly tailored solution for a specific situation.
So it's always about finding the best solution for a specific problem under specific conditions. And it sounds like this concept pops up in just about every field imaginable.
It absolutely does, which highlights their next characteristic, interdisciplinary nature. Optimal forms truly transcend traditional disciplinary boundaries. Lillian's work points out that they appear consistently in, well, you name it, mathematics, physics, biology, computer science, engineering.
Pretty much everywhere.
Pretty much. And they don't just exist within these fields. They often act as bridges between abstract theoretical concepts and real-world applications. They demonstrate a profound underlying interconnectedness across what might seem like vastly disparate areas of study. It's almost like a universal language of efficiency, spoken in many different dialects.
A universal language, I like that. And finally, there's dynamic adaptability. This one feels almost contradictory at first glance. If a shape is optimal, perfect, why would it need to adapt?
It's a fascinating paradox, isn't it? But this characteristic suggests that in certain cases, optimal forms possess the ability to adapt or even evolve over time, specifically in response to changing conditions.
Ah, so optimality isn't always static.
Not always. This adaptability is particularly evident in natural systems, right? Where survival often depends fundamentally on the ability to adjust to a shifting environment. Think evolution.
Hook.
We also see it in how complex mathematical models respond dynamically to varying parameters. If you change an input, the optimal output might shift. So this dynamic adaptability underscores the resilience and versatility of optimal forms. From the self-organizing patterns of biological organisms like slime molds finding the shortest path,
Right.
to the evolving structures of certain mathematical models, optimal forms demonstrate their capacity to remain effective and efficient even as their environment or parameters shift. It's like a design that learns and grows, always seeking that perfect balance in a shifting landscape, constantly refining its optimality. 2. Nature's blueprints and historical insights.
That concept of dynamic adaptability is really compelling. It suggests a kind of living, breathing perfection rather than something fixed and static. Now, let's talk about how this plays out in the real world, maybe starting with nature itself, because this is where it gets truly captivating, I think. Nature, in its incredible wisdom, seems to intuitively use optimal shapes to solve its own complex problems. It's almost as if the universe is the ultimate master engineer, wouldn't you say?
That's a beautiful way to put it. Nature is certainly the original optimizer.
Just think about minimal surfaces, like those formed by soap bubbles. If you've ever, watched a kid blow bubbles, you're looking at a perfect, ephemeral illustration of an optimal form right there.
Fleeting perfection.
Exactly. They naturally minimize surface area for a given volume of air. It's a direct consequence of surface tension acting equally across the film. It's an elegant, spontaneous solution to a physical constraint, needing no conscious effort at all, just physics doing its thing.
And doing it perfectly. Or consider the mesmerizing golden ratio spirals. These appear just ubiquitously in natural phenomena.
The Nautilus shell is the classic example, right?
That's the one everyone knows, yeah.
Mm.
But also the swirling arms of a hurricane seen from space, or even the arrangement of seeds in a sunflower head.
Huh. Sunflowers, too.
Absolutely. Look closely next time. These spirals aren't just pretty patterns. They consistently showcase what Lillian calls an optimal balance between growth and form, the linear and nonlinear. The inherent mathematical constant, the golden ratio, guides their growth and structure, ensuring maximum packing efficiency for the seeds or ideal distribution as the form expands outward.
So nature's been designing optimally for, well, eons. But this quest for the best shape isn't just a modern scientific thing, is it? It seems deeply ingrained in human history, long before we had complex math or computers.
Oh, definitely.
Take that famous ancient anecdote of Dido's problem. You know the story. Dido, the legendary founding queen of Carthage.
Vaguely refresh my memory.
Well, the story goes she was given this seemingly unfair offer. She could only claim as much land as she could enclosed with a single ox hide. Seems impossible, right? Just one hide.
Right, sounds like a tiny clod. What does she do?
What she did next was brilliant. Apparently, instead of just laying the hide down flat, she strategically cut it into incredibly thin strips, tied them end to end, creating this astonishingly long line.
Ah, clever. Maximizing the perimeter.
Exactly. Then, she used this elongated line to enclose the maximum possible area by forming a semicircle along the natural coastline, effectively using the sea as one boundary.
Genius. Using a natural constraint to her advantage.
Totally. This ingenious solution demonstrates that the quest for optimal solutions isn't new at all. It's a fundamental aspect of human problem solving, way before formal mathematical analysis existed. It highlights an intuitive grasp of efficiency.
Absolutely. That deep-seated desire to get the most out of limited resources, which is, a core tenet of optimal forms. It's about leveraging constraints not just as limitations, but as opportunities to achieve peak performance. Finding the loophole the best way. 3. The language of structure. Mathematical foundations.
Okay, so we've seen nature's elegant blueprints like the bubbles and spirals and even ancient human ingenuity with Dido. But how do mathematicians actually, quantify this idea of perfection? How do they rigorously define and evaluate optimal forms? This is where the language of structure, those profound mathematical foundations, really come into play.
Right, because intuition is great, but science needs rigor.
Exactly. So one key way, as the Marvels of Optimal Shapes explains, is through quantifiable metrics. Evaluating optimal forms isn't just a matter of subjective judgment, like saying that looks efficient.
No, it has to be measurable.
Right. It often involves precise, measurable criteria. Think about trying to minimize energy consumption in a complex engineering system, like designing a more fuel-efficient car,
Okay.
or maximizing information storage density on a computer chip, or even optimizing computational efficiency in a sophisticated algorithm, making it run faster using less power. These aren't vague goals. They're all objective, quantifiable criteria. They give us a clear, undeniable way to assess what optimal truly means in a given context. Numbers don't lie, basically.
Precisely. And it's important to realize that this rigor isn't always confined to the three physical dimensions we typically experience day to day.
Ah, right. Things get weird dimensions-wise.
They can. The source material discusses multidimensional optimization, where optimal forms can exist and be conceptualized in spaces far beyond just length, width, and height.
Okay, like more than 3 dimensions. How does that work?
Well, think about optimizing a system with many variables, maybe temperature, pressure, flow rate, material strength, cost, dozens of factors. The optimal shape isn't a physical shape anymore, but a point in a high-dimensional parameter space that represents the best balance of all those factors.
I see, so the shape is more abstract.
Exactly. This idea is absolutely crucial for addressing complex relationships among multiple variables. It's particularly relevant in fields like optimization theory, where solutions often extend far beyond simple geometric considerations, grappling with abstract spaces of possibilities to find the most efficient pathways or configurations.
And then there are fractals and self-similarity. This is visually stunning stuff. I mean, Mandelbrot sets and things like that.
Oh yeah, fractals are captivating. These are forms that exhibit fractal characteristics, meaning they display self-similar patterns at different scales.
Like Russian dolls, kind of.
In a way, yeah. What's amazing is that whether you zoom way in or zoom way out, you often see the same intricate design repeating almost infinitely. Think of a coastline on a map. The jaggedness looks similar whether you view a mile or 1,000 miles.
Right, right.
And this self-similarity isn't just beautiful. It often leads to structures that efficiently utilize space and resources. We see it everywhere. The branching patterns of a fern leaf, or trees, or blood vessels, the intricate structure of human lungs maximizing surface area for gas exchange.
Wow, lungs too.
Absolutely. Or the complex shapes of coastlines we mentioned. It's nature using this repeating pattern strategy for efficiency.
So this raises a really important question, doesn't it? What does it mean for a shape to be optimal across such vastly different scales, from the microscopic branching in our lungs to the cosmic scale of galaxy distributions?
That's the profound question fractals pose. And they offer a powerful and elegant answer. They demonstrate how a single underlying mathematical principle or rule can generate incredible efficiency and profound elegance at every single level of observation. It reveals a deep connection between abstract mathematics and the tangible physical world all around us. Scale invariance, you could call it, from theory to application. Cutting-edge optimal forms in technology and science.
Okay, so we've explored the foundational ideas. We've seen how nature and even ancient minds intuitively grasp this idea of optimality. Now let's pivot to the bleeding edge. This is exciting. Let's explore some incredible cutting-edge optimal forms that are actively shaping our future right now, from medicine to aerospace and beyond. These aren't just theoretical constructs anymore. They're real prototypes, tangible manifestations of this new language of form that's revolutionizing industries with precision design.
Yeah, this is where the theory hits the road, so to speak.
Definitely. Let's kick things off with a real game changer in medical tech, the magnetic flux toroid used in advanced MRI technology. Imagine a super efficient, donut-shaped magnet, that's the toroid part, designed to pack way more diagnostic punch than ever before.
More bang for the magnetic buck.
Exactly. The key insight here is that this specific toroidal shape isn't just arbitrary. It's meticulously engineered to hyperconcentrate magnetic energy, the magnetic flux, within its core. This gives doctors unprecedented clarity when looking inside the human body.
That's right. This innovative toroid is crafted to optimize magnetic flux density specifically for improved MRI performance. That unique toroidal shape allows for a far more efficient and intensely concentrated magnetic field compared to, say, traditional cylindrical magnet designs.
Okay.
And this, in turn, significantly enhances its ability to generate and manipulate those magnetic resonance signals we use for imaging. It aims to overcome the limitations that traditional MRI systems often face, potentially offering much finer detail and maybe even faster scan times.
And the incredible precision behind this isn't magic. It's pure mathematics, right? There's an equation for this.
There is. It involves calculating the magnetic flux, represented by Or, over the entire surface of the toroid. Essentially, it's adding up the strength of the magnetic field passing through every tiny bit of that donut's surface. A higher flux means a more powerful, concentrated field.
Got it. So the math ensures we're maximizing every bit of that magnetic field, leading to those crystal clear, detailed images essential for diagnostics and cutting-edge medical research.
Precisely. The primary objective is optimizing MRI for superior visualization of anatomical structures, maybe even subtle pathological conditions, allowing for earlier and more accurate diagnoses.
Makes sense.
But the applications for this kind of optimized magnetic field could extend beyond just medicine. You could potentially see it used in highly sensitive magnetic sensors, or even in developing novel materials with unique magnetic properties.
But there must be challenges.
Oh, absolutely. The challenges are significant. Fabricating these toroids with extreme precision, calibrating them perfectly, and seamlessly integrating them into the complex machinery of existing MRI systems isn't easy. Plus, there's ongoing research into discovering new materials with even higher magnetic permeability to make these toroids even more powerful. It's a constant push.
So we've seen how this concept boosts medical imaging. But what happens when we try to engineer this kind of perfection into, say, artificial intelligence? That brings us to something truly fascinating. The neural network sphere, NNS, in advanced AI systems. It's like an attempt to literally build a more efficient brain.
That's a good analogy. The NNS is designed to emulate the complex, interconnected neurons we find in biological brains. But crucially, it arranges them in a spherical configuration, a 3D ball of neurons, essentially.
So instead of a flat layer.
Exactly. This three-dimensional structure, the sphere, is thought to dramatically enhance information flow and processing compared to traditional, flatter architectures. By optimizing neuron distribution spherically, it allows for potentially far more efficient communication pathways and computation. Think of it like taking a sprawling, flat city map and folding it into a compact, connected globe. It inherently shortens many of the possible routes between points.
Okay, shorter connections, faster processing. And the math behind how these artificial neurons think or activate.
That's often captured by functions like the sigmoid activation function. It's a critical component, essentially acting like a mathematical switch that models how an artificial neuron activates. It takes an input signal and smoothly maps it to an output, usually between 0 and 1, providing that nonlinear transformation, which is absolutely crucial for the network to learn and recognize incredibly complex patterns. Without nonlinearity, AI wouldn't be nearly as powerful.
And the spherical shape itself helps.
The thinking is that the spherical context truly maximizes connectivity between these artificial neurons. The inherent curvature allows for more efficient, potentially shorter communication pathways. This could reduce both the physical distance signals travel and the time delay, the latency, in signal transmission.
Which means faster AI?
Hopefully. Enhanced computational efficiency and significantly faster processing speeds. The potential applications are broad and impactful. Cutting-edge image and speech recognition, advanced natural language processing, and the development of highly responsive autonomous systems like self-driving cars or robots. It's particularly well-suited, theoretically, for processing complex volumetric data like 3D scans and making rapid, real-time decisions.
But again, challenges.
Always. Scaling these spherical networks up to massive sizes, ensuring their energy efficiency because computation takes power, and managing the sheer complexity of training them effectively remain significant hurdles for AI researchers. It's still an active area of development.
Okay, shifting back into medicine for a moment, we have the molecular origami helix. This sounds like something straight out of science fiction. An intricately folded helix, like a spiral staircase, but at the molecular level, engineered to be an optimal platform for delivering drugs with extreme precision.
It truly is mind-boggling stuff. This molecular helix is crafted using advanced nanotechnology, taking direct inspiration from the ancient Japanese art of origami paper folding.
Right.
But here, it allows for incredibly precise folding and unfolding at an atomic scale. The helical structure itself is designed to encapsulate therapeutic agents, like specific chemotherapy drugs, inside its folds.
It's like a tiny locked container.
Exactly. And it facilitates their controlled release only upon reaching the exact target site within the body. This release can be triggered by specific biological cues, maybe a change in pH levels found near a tumor, or even by external stimuli like light or ultrasound. The ultimate goal is to dramatically enhance the drug's efficacy, making sure it hits its target, while simultaneously minimizing harmful off-target effects on healthy tissues. This is a crucial need in precision medicine, especially for powerful drugs with lots of side effects.
And the design relies heavily on math, I assume.
Absolutely vital. Mathematical modeling is used to optimize these tiny structures. Imagine complex equations that calculate and minimize the total energy of the system to ensure its stability during transit through the body. These models account for everything: the strength of the covalent bonds holding the molecule together, the strain energy involved in folding it, the various intermolecular forces like van der Waals or hydrogen bonding that keep it folded, and even using probability to understand its dynamic nature under different conditions.
So the math predicts how it will behave.
Precisely. These aren't just abstract numbers, they are the blueprints that guide the design of robust and reliable drug delivery systems, predicting their behavior under different physiological conditions.
The potential seems enormous.
Oh, it's potentially transformative. It could represent a paradigm shift in precision medicine, promising much better outcomes for complex and challenging diseases like cancer by ensuring the drug hits only the cancerous cells, minimizing damage to healthy tissues and those debilitating side effects of traditional treatments.
But the hurdles must be huge, too.
They are. Significant hurdles remain, including the scalability of production, making enough of these consistently, the complexities of manufacturing these incredibly tiny, precise structures, and, of course, ensuring complete biocompatibility, making sure the body doesn't reject them or have adverse reactions. Researchers are constantly refining the fabrication techniques and optimizing the folding and unfolding mechanisms to try and make this a widespread reality.
Okay, moving on from tiny robots, let's consider the smart nanofiber mesh for advanced respiratory protection. This isn't your average N95 mask. We're talking about a mesh of intelligent nanofibers designed for optimal air filtration, with the built-in ability to dynamically adapt to changing environmental conditions.
Right. Think of it as a mask that actively responds to its surroundings. This innovative mesh is constructed from nanofibers threads that are literally at the nanometer scale, incredibly thin.
Way thinner than a human hair.
Oh, vastly thinner. And they're intricately woven together to create an extremely high surface area within the mesh structure. This allows for incredibly efficient capture of even the tiniest airborne particulate matter, things like viruses, bacteria, smoke particles, or industrial pollutants.
But what makes it smart?
What makes it smart is the incorporation of miniature sensors and possibly even actuators directly into the mesh fabric. These components can intelligently respond to real-time variations in air quality. For instance, sensors could detect a sudden spike in pollution levels and trigger actuators to maybe adjust the pore size of the mesh for better filtration, or activate an additional filtering mechanism only when needed.
That's amazing. And the math helps design this.
Definitely. There are mathematical formulations to calculate its filtration efficiency, basically, how well it captures particles. This depends on factors like the properties of the nanofibers, the structure of the mesh, and the concentration of particles in the air. Other equations describe how the embedded sensors respond to changes in air quality over time.
So it's all optimized.
Exactly. These mathematical models allow for the optimal design of these meshes, balancing maximum particle capture with minimum breathing resistance, the pressure drop. It's about finding that sweet spot between effective protection and user comfort, ensuring both efficiency and making it actually wearable. Optimization techniques like genetic algorithms or machine learning might even be used to fine-tune the design.
Where would we see these used?
The applications are quite broad, potentially in various advanced respiratory protection devices, high-performance masks for healthcare workers or people in hazardous industrial settings, maybe even sophisticated air filtration systems for homes, vehicles, or public spaces.
Challenges here too, I bet.
You bet. The primary challenges lie in the seamless integration of these smart features directly into the nanofibers without compromising the mesh structure, ensuring the scalability of their production, making large quantities affordably, and guaranteeing their long-term durability and reliability in diverse environmental conditions, wash after wash, use after use. It's about building a mask that truly knows its environment and lasts.
Okay, one more from the cutting edge. In the realm of advanced construction materials, we have the carbon nanotube scaffold, CNTS. This is described as a complex three-dimensional scaffold composed of carbon nanotubes, specifically designed to achieve an optimal strength-to-weight ratio, basically making materials way stronger but also lighter.
That's the holy grail in materials science. Awful. The CNTS leverages the truly extraordinary mechanical, thermal, and electrical properties inherent to individual carbon nanotubes. These things are incredibly strong, stronger than steel, yet incredibly lightweight. The intricate three-dimensional arrangement of these nanotubes within the scaffold structure is key. It's designed to ensure superior overall strength, remarkable flexibility, and exceptional structural integrity for the composite material. Imagine a material that's mostly empty space internally, but is incredibly rigid and tough due to this precisely engineered internal architecture. It has a very high surface area and a highly interconnected network of these tiny, powerful tubes reinforcing everything.
And math helps predict its strength.
Yes, mathematical expressions are used to model its behavior. For example, calculating the elastic potential energy stored in the bonds between the carbon atoms within the nanotubes and how the tubes interact within the scaffold. These formulas help engineers predict how the scaffold and the material it reinforces will deform under stress and how stable it will be under various loads. It ensures it can withstand immense forces without breaking or buckling.
So the main goal is that strength-to-weight ratio.
Primarily, yes. The objective is to achieve that optimal strength-to-weight ratio, which makes CNTS incredibly attractive for fields like civil engineering, potentially enabling high-strength, lightweight, and more sustainable buildings or bridges. And definitely for aerospace applications pushing the boundaries for next-generation aircraft or spacecraft that are both significantly lighter, saving fuel, and more durable.
What's holding it back from being everywhere?
The main hurdles currently remain the scalable production methods for high-quality carbon nanotubes. It's still hard to make large quantities consistently and cheaply. And their cost-effective synthesis and integration into bulk materials. Bringing CNTS technology into mainstream construction and manufacturing requires overcoming these significant economic and production challenges. However, the potential benefits in terms of material performance, energy efficiency, and overall sustainability are immense. It truly promises a potential new era in materials science if we can crack those problems. The abstract and the unseen. Optimal shapes in deeper dimensions.
Okay, that was a whirlwind tour of some really tangible, cutting-edge optimal shapes. Amazing stuff. But now, let's peel back another layer, maybe get a little more abstract. What happens when optimal shapes aren't just about physical form, about length and width, but about how things are connected or twisted or linked together in abstract spaces? This gets truly mind-bending, doesn't it? We're venturing into the fascinating realm of topology now.
Exactly. Topology is often called rubber sheet geometry. It studies the properties of space that are preserved even if you stretch, twist, or bend the space, as long as you don't tear it or glue bits together. Connections matter more than exact shape.
Okay, so take something as seemingly simple yet weird as the Mobius strip and related twists. You know, that single-sided twisted loop that always feels like a magic trick.
A classic topological object.
Right. Apparently, recent mathematical investigations, notably by a mathematician named Richard Schwartz, have focused on minimizing the material, whether it's paper or rope or string, needed to create specific shapes, like the Mobius strip. His work precisely determined the least length a rectangle must have to be twisted into a Mobius strip. Which sounds esoteric, but it really emphasizes the crucial role of a rectangle's aspect ratio, its length versus its width, in achieving that optimal, most compact twisted shape.
It's about finding the most efficient way to make that twist. And he didn't stop there. Schwartz also identified the optimal shape for just a twisted paper cylinder, which might sound mundane, but it's another fantastic example of how studying these limiting shapes, the most extreme or efficient versions, helps us understand optimal aspect ratios for different kinds of twists and constraints.
And he looked at more complex twists, too.
Yeah, even more fascinating. In exploring a three-twist Mobius strip, which is even harder to visualize, he revealed some really surprising limiting shapes. He called them the crisscross and the cup. These aren't just mathematical curiosities. They highlight the truly unique topological properties and complex behaviors that emerge when you introduce more twists. It pushes the boundaries of what we thought was possible with just a simple strip of paper, mathematically speaking.
Okay, so beyond twisted strips, what about knots? Mathematicians like Elizabeth Dan have delved into optimal trefoil knots. Knots might seem like a simple, everyday thing tying your shoes, but mathematically, they're incredibly complex topological objects.
Definitely. Knot theory is a huge field.
So she explores optimal shapes for knots, specifically the trefoil knot, which is like the simplest non-trivial knot, right? Like a basic overhand knot joined end to end, or a simple pretzel shape.
That's the one.
Her work apparently shows how different precise methods of tying, say, flat ribbons into trefoil knots can significantly improve their length to width ratios, making them more compact and, I guess, mathematically efficient.
Exactly. It's about minimizing the amount of ribbon needed for a given thickness of the knot. And this study extends beyond just flat ribbons to thinking about actual three-dimensional ropes, determining the absolute minimum length required for a physical rope of a certain thickness to form a perfect, optimal trefoil knot without any slack or unnecessary loops.
Okay, interesting, but does this have any practical application? Minimum rope length for a knot?
Surprisingly, yes. What's particularly insightful and connects this abstract math to our world is the real-world application of these principles in fields like molecular biology, specifically in DNA modeling.
DNA knots.
Exactly. DNA strands inside our cells are incredibly long and packed into tiny spaces, so they often get tangled and knotted. Understanding how these strands knot and unknot is absolutely crucial for fundamental processes like DNA replication and repair. So these mathematical insights into optimal knot shapes, the most efficient ways to form or unform them, have profound practical significance for understanding the mechanics of these vital molecular structures. It's not just theoretical anymore.
Wow. Okay, now we're also venturing into truly theoretical concepts, things pushing the very limits of our understanding. Like the singular quantum flux sheet, SQFS. This is described as a novel topological construct, a theoretical sheet characterized by the manifestation of singularities, weird points in the distribution of quantum flux. It explores the intricate interplay between topology, the shape of space, and quantum mechanics. Sounds heavy.
It is pretty abstract, yeah.
Yeah.
The SQFS is defined within the highly complex realm of quantum field theory, where fundamental particles and forces are described as excitations of underlying quantum fields. These fields are represented mathematically as operators. Its singularities are points or regions within this theoretical sheet where the quantum flux, think of it like quantum energy flow, behaves in incredibly non-trivial ways. Imagine areas where the quantum energy gets infinitely dense or strangely twisted or discontinuous. These points are often characterized by something called a topological charge, which is a mathematical way of saying the quantum field has a non-trivial winding or twisting pattern around these specific points, like a tiny quantum vortex.
And the math behind this must be intense.
Oh, yeah. The rigorous underpinnings for understanding this draw from advanced fields like differential geometry, which describes the smooth structure of space-time itself, algebraic topology, which deals mathematically with connectivity, holes, and fundamental shapes, and functional analysis, which provides the sophisticated tools needed for precisely defining and manipulating these quantum field operators. It's truly pushing the boundaries of quantum topology and our fundamental understanding of the relationship between geometry and quantum reality. Very theoretical, but potentially profound.
Okay, let's try another complex one. The fractal harmonic lens, FHL. This sounds incredibly advanced lens, like for light or sound, but with a fractal geometry designed for the harmonic focusing of waves. What does harmonic focusing mean?
Good question. The FHL is a groundbreaking concept that promises significant advancements in wave manipulation technologies, whether that's light waves, sound waves, or even other types. It utilizes an intricate fractal pattern, remember, self-similar at different scales, which is defined by an iterative mathematical process. This complex geometry is then applied to the fundamental wave equation, the math that describes how waves propagate. Harmonic focusing means the goal is to focus the waves in a way that preserves their perfect synchronized patterns, their coherence, even as they pass through the lens and are concentrated to a point. Standard lenses can sometimes distort the wave structure. The fractal geometry introduces a level of complexity that allows for this potentially superior focusing, but it also requires advanced numerical methods and optimization techniques like genetic algorithms to design the fractal pattern just right to maximize the intensity or amplitude of the focused wave.
And where might this be useful?
The potential applications are vast, maybe significantly improving efficiency in telecommunications by focusing signals more precisely, or in acoustic technologies like ultrasound imaging or targeted sound delivery, and definitely in optics, perhaps leading to revolutionary new types of microscopes, telescopes, or laser systems that allow for unprecedented control over light waves. It's about shaping waves with incredible precision using these optimal fractal designs.
It's truly incredible how these concepts weave through so many different scientific fields. But if we step back for a moment, how does this idea of optimal shapes tie into the maybe less intuitive theme of economics and social structures? It seems like a huge leap from quantum physics or fractal lenses to, like, the marketplace.
It might seem like a leap at first glance, but that's the beauty and the power of the concept of optimal forms. They aren't just restricted to physical objects or natural phenomena. They can potentially model complex systems like economies and societies, perhaps guiding us towards more equitable, efficient, and sustainable futures.
Really?
Well, consider the concept proposed in the source, the economic equilibrium torus. This is described as a novel, torus-shaped, donut-shaped, again, economic model designed to achieve sustainable equilibrium.
Okay, a donut-shaped economy. What does that signify? Why a donut?
It's grounded in general equilibrium theory from economics, where various market forces interact to achieve a balance between supply and demand. The torus shape itself isn't arbitrary in this model. It profoundly embodies the cyclical nature of economic activity production, consumption, investment, flow of money, reflecting the inherent interconnectedness and dynamic feedback loops within a real economy. It visualizes the continuous flow.
I see. So it's a visual metaphor for the flow.
Exactly. And this model is informed by advanced economic theories that consciously prioritize sustainability and social justice, not just growth at all costs. It explicitly incorporates mechanisms to address negative externalities, things like pollution or resource depletion that traditional models often ignore. It aims to promote resource conservation and actively mitigate economic inequality. Sophisticated mathematical analysis and computational simulations are used within this toroidal framework to explore alternative economic scenarios and the potential impacts of different policy interventions, all aiming for long-term economic stability and well-being for everyone involved, not just maximizing GDP.
That sounds like a truly holistic, maybe more ethical approach to modeling an economy. And then there's another one, the circular resource flow mandala. Again, a really fascinating image for an economic concept, mandala.
It is a powerful image. This is conceived as a mandala-shaped model specifically for circular economies. Economies designed to eliminate waste and continually reuse resources. It's intricately designed to optimize resource flow, minimize waste generation down to zero if possible, and also address imbalances in income distribution.
So the mandala shape represents the circularity.
Precisely. The mandala structure itself symbolizes interconnected cycles and harmonious patterns, signifying the continuous and regenerative nature of resource flows, much like you see in closed-loop natural ecosystems. It's a direct contrast to the traditional linear take-make-dispose economic model.
How does it work in practice, conceptually?
It incorporates ideas like intelligent resource tracking using technology, sophisticated data analytics to understand flows, and predictive modeling to minimize resource extraction in the first place, vigorously encourage reuse, repair, and recycling, and dramatically enhance the entire system's resilience against shocks or shortages.
So it's about making waste obsolete, essentially.
That's the core idea. Waste reduction is paramount and is integrated at every single stage, including promoting circular design principles right from the very beginning of product development, using eco-friendly packaging, and developing advanced waste-to-resource technologies. Crucially, it also emphasizes promoting equitable distribution of the economic benefits generated within this circular system through things like inclusive business models, supporting social enterprises, and ensuring fair compensation for all participants. It envisions an economic ecosystem where each component actively contributes to maintaining overall balance and health, contributing positively to ecological restoration and biodiversity, a truly regenerative system.
And finally, in this vein, we have the inclusive marketplace hyperdimensional helix. Wow, that's a mouthful, but it sounds incredibly futuristic and complex.
It is definitely pushing the boundaries of conceptual modeling. This is envisioned as a visionary helical spiral staircase, again, hyperdimensional economic marketplace structure. The key emphasis is on inclusivity, fair trade practices, and accessibility for everyone, across what the model calls hyperdimensional economic landscapes.
Hyperdimensional, like the multidimensional optimization we talked about earlier.
Exactly. Mathematically, its helical structure deliberately introduces a multidimensional aspect, reflecting the vast diversity of economic dimensions and interactions, not just price, but maybe social impact, environmental cost, ethical sourcing, accessibility, community benefit, all visualized simultaneously. It would involve intricate geometric equations and transformations to capture these dynamic, multifaceted economic relationships.
So each turn of the helix represents something different, another dimension.
Yes, that's the interpretation. Each turn of the helix could symbolize a unique economic dimension, representing the diverse range of goods, services, values, and stakeholders involved in a truly modern, complex economy. It profoundly emphasizes the interconnectedness of these dimensions and the crucial importance of inclusivity and collaboration for achieving genuinely sustainable and equitable growth. It's pushing the very boundaries of economic modeling into new, more complex, hopefully more just territories.
Okay, prepare yourself, because this next part truly blew my mind when I first encountered it in Lillian's work. We've talked about shapes in nature, in engineering, even abstract economic models. But can numbers themselves have optimal shapes? I mean, how on earth do you even visualize that? Numbers are abstract.
It's a fascinating and counterintuitive concept, isn't it? But it bridges abstract number theory, the study of integers and their properties, with concrete geometry. Mathematicians are indeed visualizing the very essence of number theory through geometric forms. It's about giving a tangible shape to abstract numerical relationships and patterns.
Okay, I need examples. Let's start with the Riemann surface ribbon, RSR. The text describes it poetically as a delicate, iridescent ribbon unfurling through a realm where mathematics and imagination intertwine. Sounds beautiful, but what exactly is it visualizing?
This ribbon-like surface visually represents something called Riemann surfaces. These are absolutely crucial in the study of complex analysis, a branch of mathematics dealing with functions of complex numbers involving the square root of -1. The ribbon visually embodies the intricate, often multi-layered nature of these complex functions.
Macaulay layered.
Yeah, imagine a function where one input can lead to multiple outputs. The Riemann surface helps visualize how these different outputs connect. Each fold and twist on the ribbon represents what mathematicians call a branch point, or a singularity. These are special points where the function behaves in a unique way, often causing the fabric of the surface to intersect or overlap itself, creating these mesmerizing patterns of layered sheets.
And the colors.
As the colors on the ribbon morph and shift along its length, they visually reflect the values or properties of the complex functions being plotted onto the surface, making the abstract variations visible.
And what about the ribbon momentarily separating into strands before merging back together?
That illustrates a key concept called analytic continuation. Imagine the ribbon momentarily separating into multiple distinct strands. These represent different sheets or branches of the multi-valued Riemann surface. When they seamlessly merge back together, it visually shows how a complex function, perhaps initially defined only on a small region of the complex plane, can be smoothly extended or continued to a much larger domain, even across those tricky branch points where the function seems to split. It's a profound visualization of complex, multi-valued mathematical concepts, transforming highly abstract ideas into a beautiful, almost tangible geometric form.
Okay, that's starting to make a bit more sense. Then we have the golden ratio geodesic dome, GRGD. This is a geodesic dome, those dome structures made of triangles, like at Epcot.
Exactly like that. Buckminster Fuller's designs.
But here, the proportions of its triangular facets precisely adhere to the golden ratio, that famous number phi, approximately 1.618. I'm guessing this isn't just about making it look pretty.
You're right. It's far more than just aesthetics, although it certainly contributes to that. It fuses geometric elegance with profound structural harmony and efficiency. The dome is essentially a network of triangles arranged on the surface of a sphere. In the GRGB, for each triangular face, the side lengths are related by that precise golden ratio. Typically, the longer side is about 1.618 times the shorter side.
Why? What does that do?
This isn't arbitrary. This integration of the golden ratio throughout the structure is believed to enhance the dome's structural rigidity and stability, distributing stress more evenly across the frame. While it imparts a distinct visual appeal, yes, it's also functionally beneficial. The golden ratio is renowned for its aesthetic qualities, appearing harmonious to the human eye. But here it also creates a structurally sound, visually pleasing, and mathematically informed architectural masterpiece. The mathematical symmetry derived from the golden ratio is preserved through its consistent application, making it potentially incredibly strong and efficient for its weight.
Moving on to the elliptic curve toroid, ECT. This is described as a captivating geometric structure that seamlessly integrates the elegance of elliptic curves with the toroidal or donut form. What's an elliptic curve first?
Okay, elliptic curves are fundamental objects in modern number theory and cryptography. They're defined by a specific type of cubic equation, usually looking something like y squared equals x cubed plus x plus b. Despite the name, they aren't actually ellipses.
Right, confusing name.
Very. But they have incredibly rich mathematical properties. The ECT takes this abstract algebraic equation and maps its solutions, the pairs of x, y, that satisfy the equation onto the surface of a toroid, the donut shape.
So the points on the donut represent solutions to the equation.
Exactly. The surface visually showcases all the points that satisfy that specific elliptic curve equation, giving us an intuitive understanding of what's called algebraic geometric duality. It's about how abstract algebraic structures, like the group structure on an elliptic curve, can be translated into concrete geometric shapes and properties on the torus.
What's the use of visualizing it like this?
It serves as a powerful tool for visually analyzing complex relationships and patterns in number theory related to these curves. It can help mathematicians understand concepts like torsion points, points that return to the start after being added to themselves a certain number of times using the curve's special addition law, or the rank of the curve, related to how many independent starting points you need to generate all rational points. It even offers visual insights into highly complex mathematical conjectures, like the famous Birch and Swinnerton-Dyer conjecture, which relates the rank to properties of an associated function and is one of the Clay Mathematics Institute's Millennium Prize problems. Seeing the structure can spark insights.
Next, the Mersenne prime polyhedron, MPP. This is a polyhedron, a 3D shape with flat faces, like a cube or dodecahedron whose faces directly correspond to Mersenne prime numbers. That sounds very specific.
It is, but it's a wonderful way to connect number theory and geometry. A Mersenne prime, remember, is a prime number that happens to be one less than a power of two numbers like 3, which is 2 squared minus 1, 7, 2 cubed minus 1, 31, 2 to the 5th minus 1, and so on. They are quite rare.
Okay, so how does the polyhedron work?
In the MPP concept, each face of the polyhedron is somehow labeled or associated with the exponent n from the Mersenne prime form 2 and 1. The structure of the polyhedron itself might reflect relationships between these primes. It provides a visual and perhaps even tactile representation of these special, rare prime numbers, allowing mathematicians to explore their distribution, their symmetries, and their intrinsic connection to geometric shapes. It's a fantastic example of how seemingly abstract number theory can manifest in a physical, tangible form, maybe revealing hidden patterns.
And then, almost poetically, the Fermat's last theorem tower, FLTT. This one has such a dramatic history behind its name. It's described as a tower structure where each level represents a potential solution to Fermat's last theorem. That theorem, famously stated by Pierre de Fermat in the 17th century, claims there are no positive integer solutions to the equation a to the power n plus b to the power n equals c to the power n for any integer value of n greater than 2.
Right. A simple equation, but notoriously difficult to prove. It took over 350 years.
Exactly. So this tower visually embodies the solutions that famously eluded mathematicians for centuries, literally driving some to despair, until Andrew Wiles finally presented his monumental proof in 1994. Each level of the conceptual tower could correspond to a unique set of integers, ABC, and an exponent n that mathematicians investigated or tried to find as a solution before Wiles proved none exists for n2. So it's a tower of failures, in a way.
Or a tower of the quest. Or a tower of the quest, I think. Each level symbolizes a significant milestone or a specific case examined during that long, arduous mathematical journey towards resolving Fermat's last theorem. The levels might be labeled with the exponent n and the corresponding integer values a, b, and c arranged visually, offering a powerful spatial representation of the theorem's elusive nature and its ultimately non-existent solutions for n greater than 2. It's a beautiful conceptual homage to one of the most monumental mathematical achievements in history, celebrating the journey of discovery and the dedication required, even when the final answer is no, there are no solutions.
The non-Euclidean crystal lattice, NECL, is another intriguing concept mentioned, a crystal lattice structure, the repeating pattern of atoms in a solid, but modeled within the framework of non-Euclidean geometry. What exactly does non-Euclidean mean in this context? We usually think of crystals as very ordered, very Euclidean.
This takes us beyond the familiar geometry of flat surfaces and straight lines, the geometry Euclid described and that we learned in high school. Non-Euclidean geometry deals with curved spaces where Euclid's famous parallel postulate doesn't hold, meaning parallel lines might eventually meet, like on a sphere elliptic geometry, or diverge infinitely faster than in flat space, like on a saddle shape hyperbolic geometry.
Okay, so how does that apply to crystals?
The NECL explores how those regular repeating lattice formations, the fundamental structure of crystals, might arrange themselves in these curved spaces with different curvature properties rather than just flat Euclidean space. It represents a daring challenge to conventional geometric constraints we assume for materials, investigating how geometric structures might evolve and pack together under the transformative influence of these non-Euclidean principles. It provides a completely new perspective on how structures could be formed in alternative curvatures, potentially leading to hypothetical new materials with highly unusual packing efficiencies, densities, or other physical properties. It's imagining materials built on different geometric rules.
And finally, the Eulerian graph network, EGN, described as a network of nodes and edges following Eulerian graph principles. What are those?
Okay, this goes back to the famous Seven Bridges of Königsberg problem solved by Leonhard Euler in the 18th century, which basically founded graph theory. An Eulerian graph network is a geometrically profound network of nodes, points or vertices, and edges, connections or lines, that meticulously adheres to Euler's theorems. These theorems describe the conditions under which you can trace a path in a graph that traverses each edge exactly once without lifting your pencil.
Like drawing figures without retracing lines.
Exactly that puzzle. The EGN is a captivating visual testament to the structural properties defined by Euler's work. Each edge within the conceptual EGN corresponds to a part of a potential path traversing each connection exactly once. Its intricate network structure is molded to embody Euler's theorems, offering a truly vivid visual representation of the dynamic interplay between vertices and edges, showcasing an inherent elegance and complexity based on connectivity. It provides profound insights into the fundamental structural properties of networks, a critical area of discrete mathematics with countless applications today, from optimizing delivery routes and designing communication networks to analyzing social connections and even modeling biological systems. Connectivity is key. 6. The unifying vision. Design as a universal language.
Wow, okay. My head is spinning slightly, but in a good way. From the incredibly small scale of molecular helices designed for targeted medicine to grand, abstract economic models aiming for sustainability, from ancient human problems solved with simple oxides to mind-bending quantum structures and visualizing prime numbers as polyhedra-optimal shapes are genuinely everywhere. What's the big takeaway from this incredibly deep dive? What does it all mean when you put it together?
It's a lot to take in, for sure. But this journey through Lillian's The Marvels of Optimal Shapes, I think, reveals that these optimal forms encapsulate a truly rich tapestry of mathematical precision, profound scientific functionality, and often captivating aesthetic allure. They are far more than just practical solutions to specific challenges. They really are symbolic representations of humanity's relentless, perhaps innate, quest for perfection and efficiency across incredibly diverse domains.
A quest for perfection.
In essence, they serve as a profound universal language, a language that connects structure to meaning, speaking to us from the very fabric of existence, whether we're looking at a galaxy or a soap bubble.
It's incredible to see how these fundamental concepts weave through so many different fields, from the most tangible engineering problems to the purely abstract realms of math and philosophy.
Indeed. And Lillian argues they consistently manifest several key aspects. First, that mathematical precision. They embody rigorous analysis and optimization techniques that maximize efficiency or performance or utility, always within clearly defined constraints. They represent the culmination of precise mathematical principles and often astute engineering expertise, ensuring every bit of potential is leveraged.
And they demonstrate a profound scientific functionality, wouldn't you say, based on how the world works?
Yeah. Absolutely. Optimal forms are tangible manifestations of underlying natural laws and fundamental physical or biological phenomena. They harness scientific knowledge to achieve the most optimal outcomes possible within those laws. Whether you consider the incredibly refined aerodynamic shapes of a bird's wing evolved over millennia, or an aircraft wing designed using fluid dynamics, or the intricate molecular structures in advanced materials engineered for specific properties, they embody the principles of efficiency derived directly from deep scientific inquiry and observation. Nature optimizes, and we learn from it.
And there's always that undeniable aesthetic allure that keeps coming up.
Precisely. It's hard to ignore. Optimal forms often captivate the human imagination with their inherent beauty, their symmetries, their balance, and their undeniable elegance. They seem to transcend mere functionality to evoke a deep sense of wonder and admiration in us. They reflect the harmony and balance that seems so inherent in nature's most successful designs. It's almost as if their very efficiency inherently leads to a form of beauty that resonates with us.
So all of this, taken together, points to something even bigger, something you mentioned earlier. Lillian calls it a universal design intelligence. What exactly does that mean?
That's the really big picture idea, I think. This refers to the embedded intelligence that appears, arguably, to be present across both natural and artificial systems. It's the underlying drive or tendency that gives rise to optimal forms through processes like inherent pattern recognition, constant adaptation and evolution, and achieving states of energetic resonance or stability.
So intelligence in the system itself.
In a way, yes. It suggests that there is an underlying logic and an undeniable elegance embedded in the very fabric of the universe itself. These forms are not just intellectual constructs that we humans invent out of thin air. They are, perhaps in a profound way, mirrors reflecting that latent intelligence within nature and, indeed, reflecting the potential for intelligence within ourselves when we seek optimal solutions. They speak to a fundamental order, an inherent drive towards efficiency and elegance in the cosmos.
Oh, wow. What an incredible journey we've been on. You've seen today how, from the tiniest molecular helix designed for precision medicine, aiming to cure disease at the cellular level,
Right.
to grand, abstract economic models striving for a more sustainable and equitable world.
Yeah.
And from ancient problems solved with the simple ingenuity of cutting up an oxide, to mind-bending quantum structures and visualizing the deep patterns of numbers as geometric shapes, optimal forms are truly everywhere around us and within us. They are constantly guiding efficiency, informing function, and often creating profound beauty. It's truly a vast and interconnected world of design, often hidden in plain sight until you start looking.
And this deep dive, I really hope, reveals a fundamental truth Lillian points towards, that there seems to be an inherent intelligence and a deep, elegant logic embedded in the fabric of the universe itself. These optimal forms, as we've discussed, aren't just intellectual constructs that we devise in our minds or labs. They might actually be reflections, mirrors, if you will, of the latent intelligence within nature and indeed within ourselves and our own capacity for optimal design.
That's a powerful thought.
They should inspire all of us, I think, to contemplate the inherent beauty and logic embedded in everything around us, from the mundane to the magnificent.
So as you go about your day after listening to this, maybe think about this final provocative thought. If the universe, through physics and evolution, consistently strives for optimal forms to achieve perfection and efficiency in everything it creates, what are the optimal shapes or structures we can, or maybe should, apply to our own lives? How can understanding these universal principles of efficiency, balance, and elegance inspire you listening right now to perhaps design a more efficient, a more harmonious, or maybe just a more beautiful path forward, whether that's in your own decisions, your work, your relationships, your communities, or even the complex systems we collectively build around us?
A lot to ponder there.
Definitely. Thank you so much for joining us on this deep dive into the marvels of optimal shapes. We really encourage you to open your eyes and observe the optimal shapes, and maybe the suboptimal ones too, in your own world, and to reflect on their profound significance.
Keep looking, keep questioning.
Until next time, keep exploring.